Alright, so this is going to be lecture for 9.3, but before I get into that, I want to really quickly recap 9.2. And I'm just going to frame this recap around the formulas. There are four formulas that you need to know for this 9.2 section. So we've got simple interest formula. So simple interest, I equals PRT. This is for calculating interest on a principal with a given rate and over a given time period measured in years. No compoundings here, right? That's going to set this simple. That's why it's called simple interest. You don't compound your interest multiple times per year. It's just interest in the most intuitive sense. In fact, if I asked you to find interest, how much interest an account makes with a certain amount of money based off a certain rate over a certain period of time, most of you would probably come up with this formula because it's very intuitive, just multiplying those three quantities. Then we have interest that is compounded, which is quite a bit more involved. So this is going to be A for some amount is equal to principal, so your starting point, your principal, times 1 plus r over n raised to the nt. This is with n number of compoundings, or compounds. I'll just say compoundings. That's fine. So this is the formula you use to calculate interest on an account where you are compounding the interest multiple times per year. And of course, there's different types of compounding intervals, like annually, then n would just be 1. Semi-annually means twice a year, so n would be 2. Daily means every day, so 365 times a year, so n in that case would be 365. Also, another critical difference between these two is this formula, I equals PRT, just calculates interest, not the total in the end. So if you look at example 1 in the text, in 9.2 on page 472, they've given a principal of $5,500 and then in a rate and a time, and they calculate interest as $2,337.50. So you can see that interest is not, this formula does not give you the total that they will have in their account at the end of this, principal rate and time frame. You have to go back and add it back on to the original principal. Whereas this compound interest formula does it all for you. This is not, you notice this is not an I, right? It's A for like ending amount, not just interest. Okay, so it actually calculates what the amount will be for you after you add the interest on. So if you actually wanted to find the specific interest that you earned from an account with a certain number of compoundings at a given rate over a certain period of time, you would calculate this, and then you would subtract your principal from it to find whatever the interest earned was. Okay. So the idea with this formula is the more you compound, the more money you should be earning, right? That makes sense, hopefully. But there is a limit to that. So that's where this formula comes from. So if we take our compoundings and let it approach infinity, in other words, compound the interest earned on the account, like not just daily, but every second of every minute, of every hour, of every day of the year, just continuously, even every half second, every millisecond, it doesn't approach an infinite amount of money like you think it would. It actually approaches this weird limit, and I'm not going to get into the technicality of it, but basically, like this term here, this 1 plus 1 over n, if I ignore the r for a moment, 1 plus 1 over n raised to the n, if you send n to infinity, you end up with that magical, mystical, irrational number, e. And then the formula, with some algebraic manipulation, turns into A is equal to the principal times E raised to the product of R and T. So this is for continuous. So there is no n anymore because n is now blown up to infinity. So there's no number we plug in for n. This is for continuous compoundings. Okay. All right, and then we have the last formula is APY. So all of these rates given in these formulas are going to be annual percentage rates, APRs, and they, you use the APR to calculate, interest on an account, or like a total amount on an account after some number of years. But if you wanted to know if this account was not a continuously compounded interest account, or even just a regular compounding interest account, then what would the yield be at the end of this time frame of a year? What would the percentage be on the money that I earned? What is the yield after 1 year? So say you've got a compounding savings account, this kind of situation, and it compounds monthly, so 12 times a year, so n is 12, and you've got like a interest rate of 5%. So you start with some amount of money, and you end up with a larger amount of money. It's not a 5% increase, right? Because it's being compounded multiple times per year. But what is the actual percent increase between these two accounts? What is the percent difference between these? And that's a question for what is annual percentage yield. And that's what APY is, and we have a nice little formula for calculating this annual percentage yield. It's going to be 1 plus R over N. So this part of the this formula, you notice T is missing here because this is annual percentage yield. So this is for T equals 1 for 1 year. So from this amount of money to this amount of money in 1 year, what's the percentage yield between those two? And we'll take 1 away from it, and then we'll make it into we'll turn it into a percent by multiplying by 100%. Okay. And if you think about it, all this is it's just the percentage of the interest earned. Like this right here, I can say this is P, look, if I use this formula, 1 plus R over N raised to the N, letting T be 1 here. And then how would I calculate interest? How would I calculate interest? It would be this, interest over a year. It would be this, but then minus the principal. Remember, because this gives you the end total. So if you want the interest, you take the end total and you subtract your original principal. But factor that P out, and you're left with 1 plus R over N raised to the N minus 1. Okay, so looking very similar. The difference is the principal here, but you can just divide the principal over underneath your interest, and that will turn it into a rate of interest per interest divided by the original principal. That's going to turn it into a nice fraction, and then multiplying by 100% will turn it into a percent there. So that's where that formula is coming from. You don't really need to know all of that, where it comes from, but it might help to understand where the minus 1 is coming from. And let's see, that is it for 9.2, for a recap of 9.2. Alright, so right off the bat in this section, they start off in the text with a formula for present value. This section is entitled Saving Money, so the context for these problems is going to be, again, just like an interest-bearing savings account. First formula, called present value, it's just this formula all over again. 1 plus R over N is raised to the NT. Except what we're doing is we're rearranging it to solve for the principal. So what we're doing with this first formula, which I'm going to write down in a moment, is we're looking for a way to solve the problem of saying I want some future value amount of money, and I know the percent rate and the compounding rate for my savings account, and I know how many years I want to save for. What principal do I need to put into the account to earn this end amount? Say I want $12,000 and I earn 5% and it compounds monthly, and I want to do it for 10 years. What principal is necessary in order to get me to that $12,000? How do you solve for P here? You just divide by this whole thing. P is attached to this crazy looking thing by multiplication, so we'll divide it over. And when we do that, we call it a new formula, and instead of P, we say PV for present value instead of principal. And it'll look like this. Just divide this whole thing over. So that's all present value is. It's just a rearrangement of the compounding interest formula. And just to remind you, A is going to be the future value. So in this kind of problem, when you use this formula, your end value, your future value of your account will be given. Obviously, your APR needs to be given. The compounding interval needs to be given, and the number of years needs to be given. And remember that this is an APR. The little r there, that's APR, not APY. All of these R's in these formulas are APRs, annual percentage rates. APY, from 9.2, comes from calculating a percentage increase after the money has been earned from a given APR. Okay, let's do example 1, just kind of running through a calculation. Just running through a calculation with this formula. So, and this is from the text, page 485. State College predicts that in 18 years it will take $150,000 to attend the college for 4 years. Amber has a substantial amount of cash and wishes to save money for her newborn child's college fund. How much should Amber put aside in an account with an APR of 4%, compounded monthly, in order to save or to have $150,000 in the account in 18 years? So we've got R is 4%. I'm going to go ahead and write that as 0.04. Just recalling the rule for writing a percent as a decimal, just to divide it by 100. N is 12 because they say compounded monthly. N is 12. T is going to be 18 years. So she's assuming the child, I guess, is an infant, and they'll be going to college in about 18 years. And the future value we want, the future value, which in this formula is still called A, so I'll call it A, is $150,000. Okay. $150,000. What do? We just plug it in. Okay, we just plug it in. Now, the only thing that can go wrong here is a mess up of your order of operations when you're using your calculator. So what I would do is, first of all, I would write it down, plug everything into the appropriate spots, 12 times T, so 12 times 18 there. Alright. If you are not confident in your ability to punch this into the calculator and get a consistent and correct answer, then what you need to do is do it in pieces, okay? And what I mean by that is the first thing you should do is figure out what 12 times 18 is. So punch that into the calculator. So 12 times 18, coming over here to my calculator, will give me 216. So in my next step, I'm going to have 150,000 divided by 1 plus 0.04 over 12 raised to the 216. Okay. I'm going to do this now, 0.04, so I'm doing it all in pieces. and then I'll rewrite my formula here with the last step, which will be the actual division. Now, I'm getting a crazy decimal when I do this division. It's not that crazy, but it's 0.00 and then 3 repeating. I don't want to round anywhere when I'm doing this, so I'm going to put that bar there and make sure I understand that is still a repeating number of 3s. You don't want to just round, because that'll mess up your final answer. The very small digits matter very much in a problem like this, where you've got some smallish number raised to an exponent. Every digit is going to matter here, so you don't want to round. And in fact, what I'll do is I still got all these 3s stacked in my calculator, right? On the paper, of course, I have to do something like this to get it written down, but in my calculator, they're all still there. And that was this number here. So why don't I just go ahead and add 1 to it? Because that's going to be the next step. So 1 plus this 003 repeating, of course, is just 1.003 repeating. And what do I do with that number? So let me write down where we are right now. I've got 150,000 over 003 repeating raised to the 216. That's my next step there. This number raised to the 216. This number is still in my calculator, so I'm not going to clear it out, right? Because it's still there. It's got all of the 3s there. So now I'm going to press the little button. For me, it's this button, X raised to the Y. You may have the little caret button. Whatever gets you into the exponent position in your calculator. So I'll press that, and then 216, hit enter, and I'm getting a terrible decimal number. Terrible is 2.05, blah, 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 blah. Okay, so what do I do at this point? Because I still want to hold all of those digits there. I don't want to have to round and retype it into the calculator. So what I'm going to do now is I'm going to take this number, which is the 2.05, blah, 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 blah. But the problem is I need that number to be in the denominator, right? I want to say 150,000 divided by that number. So how do I do that in the calculator if I'm doing it step by step like this without discounting, without getting rid of this crazy decimal? I want to keep it. I don't want to discard it. I'm going to hit the 1 over x button. 1 over x, or yours might be x to the negative first. And what that does is it takes a number that you have in your calculator and it flips it into the denominator, so that then you can multiply it by the thing you were trying to divide the number by. So I'll hit the 1 over x button, and that's giving me 0.487, blah, 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 blah. And then I'll multiply that by 150,000. So I got my number in the denominator by hitting the 1 over x button, and now I'll multiply by 150,000. And I'm getting 73,100 and 0.31, so I'll round to the nearest hundredth because we're talking about money. Stick a dollar sign on the front. That is the amount that she'll need to put into her account that earns 4% interest compounded monthly in order to earn over the course of 18 years $150,000. That's still a lot of money, but it's she'll earn double over the course of 18 years, right? So it's almost roughly doubling her money, a little bit more than that, but it is over the course of 18 years, which is a very long time. Okay. Now, it's much better doing all this to have a calculator that you trust and know how to use, where you can just do all this in one go. The trick is to use parentheses. If you don't have one of those calculators that shows you the fraction, then you're going to need parentheses, to use a lot of parentheses everywhere in your problem to make sure your calculator knows what you want. If you do have one of those calculators that has the little box divided by box button where you can actually see the numerator and denominator, then this should be no problem. All right. Alright, this next problem, or next formula, is coming from the problem of how much money should I be depositing monthly in order to earn a certain amount of future value amount of money. Because, that feels more realistic than this. Like, really, when someone has a baby, who really has $73,000 to just throw into a savings account in order to, just let it start collecting money? That's not the way most of us save money, right? We save money by dumping regular amounts, hopefully regular, into an account, not by dumping a huge lump sum in there. Okay. So that leads us to the next definition, the next vocab term for this, that's going to come up in this formula, and that's an annuity. Annuity. And all it is a sequence, as they put it, a sequence of regular payments made into an account or taken out of an account over time. So we'll just say regular payments. Regular meaning like consistent, like monthly. Regular payments or withdrawals. Because it can mean withdrawals too. But in this context, we're going to be talking about payments into an account. Okay, so we are in the situation where we've got some future goal in mind. We know what payments we can make each month into our account, and we want to know. Sorry, 1 second. I think I messed up I didn't say what I wanted to there. We don't know the future value, but we do know the amount of money we'll be putting into the account at regular intervals. We want to know how much money will we have after a certain number of years. Okay, and the formula is future value. So future value here is equal to the payment, which I've been saying monthly. It doesn't have to be monthly. And it's going to be the rate 1 plus r over n raised to the nt. So we see the t is back, and n is there, so that's going to be the number of times that we're well, that's still the number of times the savings account compounds, actually. And this is divided by r over n. Okay, so this formula, a little bit harder to understand intuitively. I paused the video and tried to really parse it and you may have noticed this up here is the APY formula, if you recall. It just doesn't have the percent part on it, but that is APY except for a number of years. So, it's not annual percentage yield, it's just percentage yield for some given time, but then it's divided by the APR, which is then divided by the number of payments. The N is the number of payments you're making per year, but it's pretty much always 12 because payments are typically monthly. So long story short, I could not think of a good intuitive understanding of this formula, so let's just practice using it. Let's get into using it. I also notice in example 2, the solution for part B, there's a typo, but it's very minor. I'll point it out when I start solving part B. So example 2 says to calculate future value using an annuity plan. Okay, that's exactly what this formula is for. So we've got Daigle begins placing $75 per month into an annuity savings plan when he begins receiving his first official paycheck in August of 2014. The saving plan earns 2.5% APR compounded monthly. So, what all do we have there? We have the payment is $75. We have APR, which is, remember, APR is going to be the little r, is 2.5%. That's going to be 0.025. N is going to be 12 because he's depositing his money monthly. Okay, what else do we need? We need t. We weren't given t. But part A says to determine the amount of money that Daigle will personally put in the savings plan over 10 years. So I'll say t is equal to 10 up here, 10 years. Now, the first question is not asking for the future value. It's asking for how much money is he putting into the account over 10 years, not how much money will be in the account. There should be more than what he's putting in, right? That's the point of an interest-bearing savings account, right? But they're just straight up asking for how much money will he put in after 10 years? Well, how many payments will he make? Well, he's making 12 per year for 10 years, so he'll make 120 payments over 10 years. Each payment is $75, so hopefully you're seeing what we should do there. If each payment is $75 and he's making 120 payments over 10 years, then how much will he personally be putting into the account over 10 years? We'll take the product. We'll take the product of these. Whoops. Yes, 0, 1, 6. Okay, getting 9,000. $9,000. That's not how much will be in the account after 10 years. That's how much money he's putting in over the course of 10 years. Part B now is asking for the actual value of the money in the account. So we should definitely expect it to be more than 9,000. Calculate the future value of Daigle's savings in August 2024. So they're saying August 2024, he started in August 2014, so t is still 10. T is still 10. T is still 10 because he started in 2014 and they're asking for the future value in 2024, so that's 10 years later. Alright, so future value is going to be payment times bracket parentheses 1 plus 0.025, that's R, divided by N, which is 12, the number of payments per year, raised to the 12 times T, then minus 1. So the minus 1 happens after all of this calculation. Close the brackets, and then we're going to divide by 0.025 over N. Okay, so if you're doing this piece by piece in your calculator, you're going to want to do this exponent first, which is obviously 120. You'll do this division, you'll add 1 to it, and then you'll raise it to that power of 120. So I'm going to do all of that as an intermediate step. So I'm going to have 75 times. Oh, I'll also subtract 1 from it too. That's easy enough. So I already know 12 times 10 is 120, so I won't use the calculator for that. But I will say 0.025 divided by 12. Then I'll add 1 to it. Still working inside the parentheses, so I added 1. Now I'll raise that number to 120. Okay, and then I'll take 1 away from it, minus 1. So I'm getting 75 times, and I'm going to round here just to get it on paper, but remember, you don't want to clear your calculator at this point if you're doing it piece by piece. So I've got the entire numerator here done. It's going to be, I'm rounding just for the sake of getting it on paper. I'll just say 0.2837. Okay, 2837, right? Yeah, that's just to get it on paper. And then I'm going to multiply by, and I'm going to use the rule for dividing by fractions and, keep, change, flip. Okay, so instead of dividing by this divided by this, I'm going to multiply and flip the fraction upside down. And this makes my calculation in the calculator much easier. So now I've got this number in my calculator right now without it being rounded. I'm going to multiply it by 75, then I'm going to multiply that by 12, and then I'll have that number, a big number, and then I'll divide it by this. So 0.28, etc., times 75, that gives me that, and then times 12, that gives me that. So now I've got all these numbers multiplied, and that gives me like 255, roughly. And then I'll divide by this tiny number, which should blow up my answer, and it does. I'm getting 10,212.895, so I'll round that to 90. There we go. Which is, hopefully lines up with what the book got. Yes, it did. Okay, so he put in $9,000, but this will be the actual future value after 10 years. So not that much. I mean, it's still, $1,212.90 will be what the account gave him. Okay. Now oh yes. Let me point out the solution for part B here. For part B, in the solution, you probably can't read this, but it says the APY given is 2.5%. That's not true. It's an APR. It's an APR. You'll always use APR in these formulas. Anytime you see a little r anywhere in the formula, it's APR. So this is just a typo, because they gave us, see it, yeah, you see it up here, 2.5 APR. They just accidentally wrote APY there. Also, their final answer is the difference between what he gave versus what the account gave him, so, or what the account earned. So this is what the account gave him, that $1,212.90. But that's not what the problem asks for. I don't want you to look at that solution and be like, okay, so wait, is the answer, this, or is it the difference? In part B, they said calculate the future value. That is this formula which yields this answer. This is the answer. They just went a little bit further at the end of that problem to give you a little bit more information there. Alright, examples 3 and 4 are going to be more future value calculations. I'm going to go through them a little bit quicker. Okay, example 3 says use the annuity formula to calculate the future value after 6 months of monthly $50 payments for an annuity savings plan having an APR of 12%. Alright, let's get all this down. So first of all, T is 6 months. It's not 6, right? Because T is measured in years. So 6 months is 0.5 years. You have to remember, if they ever give time in months or days or anything but years, you have to convert it to years. Monthly payments are $50. R is going to be 12%? Yeah, so 0.12 for 12%. And N is going to be 12 because these are monthly payments. So remember, N in this formula for future value deals with how many times per year are you making this payment. And since the payments are monthly, N is 12. N is 12. Even though we're only doing it for half a year, N is still going to be 12. Okay. All right. So future value is going to be that payment. And that payment times, and then we're going to have a big fraction. The formula is written as a fraction, but that rule I applied for dividing by fractions last time, at the end, we can put it up front, really, and we could say, so in our bracket here, we'll still need a bracket. We're going to have 1 plus r, which is 0.12, over n, which is 12, raised to the n times t. So 12, that's 12 dot for time, so 12 times 0.5. Okay, that's a decimal, that's a multiplication. All right, then minus 1, close the bracket, and then another multiplication here coming, and instead of r over n, which is what it was in the denominator, if we're now flipping and multiplying, it's going to be n over r. Alright, now I'm not gonna walk through all this. Tell you what, I'll just do it kind of out loud. I'll tell you what I'm punching into my calculator, because my calculator is, I'm using the Windows desktop calculator, so I have to do it kind of step by step here. So first of all, I know 12 times 0.5 is 6, so that's fine. I don't need to punch that into the calculator. So I'll do this part first, 0.12 divided by 12, giving me that. Oh right, just 0.1. Then plus 1, and then raised to, where's that button? Raised to the 6th, and then minus 1. Okay, so I've got all this contained as a crazy decimal, and then times 50, and then times 12, and then that number divided by 0.12. Okay. Giving me a future value of $307.60. Okay. So after half a year, this is how much would be in the account. How much interest did this earn? As an additional problem, well, think about, you're making $50 payments for half a year. That's 6 months. That's 50 times 6, right? 50 times 6 is going to be, that's how much money you are putting into this account. So the interest earned is only $7.60 over the course of half a year. And the reason it's such a small amount of interest, despite having a pretty big interest rate, is, well, first of all, this is only measured over half a year, when the other problems we were doing were measured over like 10 and 18 years. But also the payments are fairly small, relatively. Okay, let's do example 4. At the age of 25, Angela starts an individual retirement account, or an IRA, to save for retirement. She deposits $200 into the account each month, so immediately I know PMT is equal to $200. Also, I should note that she's 25, because when they tell you something like that, they're probably later going to tell you some other age that, you know, like they'll say, like, how much money will she have earned when she's 35? And that you'll have to find the difference of her future age versus her present age to get whatever time is. Based on past performance of similar accounts, she expects to obtain an annual interest rate, so that's APR, of 8%. So we'll just go with that, say 8% there. Part A says, how much money will Angela have saved upon retirement at the age of 65? Okay, so there it is. So, oh, by the way, N is 12, I forgot, because these are monthly payments. So how much money will she have saved upon retirement at the age of 65? Well, what is T then? She started it at 25, ending at 65, or at least that's when they're, that's what the time frame they're asking about, so T is 40 here. So, this is asking for a future value. How much money will she have saved? So let's see, we'll have payment times 1 plus R over N raised to the NT, 12 times 40 minus 1, close brackets, and then times N over R. So I'll use this form of the formula again, N over R. Okay. I'm not gonna work through this again. The only trick to this part A is just understanding that T has to be 40. I mean, the calculations, just make sure, you know, I'm not gonna keep redoing, you know, how I do these calculations, because you are probably doing them differently, so you're not gonna benefit from hearing me talk about that. So let's just make sure we're on the same page with the solution. $698,201.57 should be the answer there for part A. That's how much money she'll have saved for retirement. Okay, so this is a lot. Why is it so much? Well, first of all, her payments are fairly large. Also, her interest rate is pretty good, 8%, that's pretty good. Also, 40 years is a long time. 40 years is a long time. So, $200 per month for 40 years. Well, in fact, how much is that? That's what Part B is getting at. Part B says compare the future value to the total amount she deposited over the time period. So, how much is she putting in versus how much did she earn? In other words, like, how good really is her savings account? Well, we can say she's making $200 payments 12 times a month. 12 times a year for 40 years. Take the product of all of those. And that's going to give me, well, the book tells me I'll just do that. So, $96,000. Whoa. So that's pretty crazy, because she's only depositing this much over the course of her life. Well, over the course of 40 years, like $100,000, and yet she's going to retire with $700,000. God. I need to start a savings account or a retirement account, because that is, can you imagine being an old person with nearly $1 million to burn? Okay. So there's a nice little example that's not labeled as an example after skill check number 3 on page 490 through, so it goes page 490 through the halfway down page 491, and it's comparing two different situations, two different compound savings accounts with the same APRs but over different time frames, and it kind of outlines how powerful compound interest is. Basically, one guy starts investing early but then stops. He starts making payments early and then stops, and his account continues to earn interest. And the other guy, at the same time the first guy stops, he starts making the same payments and just continues forever making payments. And the question is, when does the second guy catch up to the first guy? And the answer is never. He never will. Because the first guy's account continues to earn interest, and despite this guy continuing to make more and more payments each month, he'll never be able to catch the first guy, even though the first guy stopped making payments after only 15 years. So that's just the power of compound interest. The growth rate is too great to overcome without making like increasingly large monthly payments. Alright, so now let's answer the question of how much monthly payment do I need to make? What is the monthly payment I need to make in order to reach a given future value? And that formula is going to be payment is, I mean, you could figure this formula out. It's going to be just this, where is it? This formula solved for payment. So basically take future value and divide this whole thing over. Divide the whole thing over. Let me get back in order here. So we're going to have that future value divided by that giant fraction, but in other words, instead of dividing by the giant fraction, we'll flip the giant fraction upside down. So in the bottom now, we'll have that 1 plus r over n raised to the nt, minus 1. And then in the top, we'll have, r over n. That's r over n, r over n. So we can't do the thing where in the future value formula, this r over n and this this thing here were swapped. So I was able to take r over n and put it over here as a multiplication instead of a division, and that's because this is a very simple fraction, just r over n. Super simple to flip upside down. Flip it upside down, it's n over r, right? Can't do that here because this is not a simple fraction that can just be flipped upside down. So no luck there, I'm going to have to leave the formula this way. So example 5, you're going to use this formula. Okay, Suppose you'd like to save enough money to pay cash for your next computer. Your goal is to save an extra $3,000 over the next 3 years. So future value is $3,000. T is going to be 3 years. Alright, what else have we got? What amount of monthly payments must you make into an account that earns 1.25 interest? So first of all, they say monthly payments, so N is 12. And they also give us that earns 1.25% interest in order to reach your goal. So 1.25 is 0.0125 as a decimal. Alright, there we go. That's all we need. So PMT, payment, is what we're looking for. It's going to be equal to future value times R over N divided by bracket parentheses 1 plus R over N raised to the N times T, then minus 1, close bracket. So I'm going to have to make use, the way I'm doing it in my calculations is I'll calculate this, then add 1 to it, raise it to 36, subtract 1, then I'll make use of that 1 over x button again to flip the number to be in a denominator. And then I'll multiply by this, 0.0125, I'll multiply by 3,000, and then I'll divide by 12. Excuse me. Okay. So if you're confused, if the calculator part is holding you back, you're going to want to make sure you learn how to use your calculator. Whatever calculator you're going to be using on the exam, make sure you figure it out. 0.0125 divided by 12 plus 1 raised to the 36, because 12 times 3 is 36, and then minus 1, that gives me that, and then I'll 1 over x to get that so that I can multiply, oh, wait, there it is, so I can multiply by it. So now I've got this flipped upside down so I can multiply by it. And I'm going to multiply things onto it, so I'll multiply by 0.0125, then I'll multiply by 3,000, and then I'll finally divide by this 12. Okay. And I'm getting $81.82. And then you may hesitate and say, wait a second, that's a really tiny number, what's going on here? But then you say, oh wait, I'm calculating payments, not a future value here, I'm calculating payments. So is this in the ballpark for a reasonable monthly payment? Yes, it is. If we had gotten like 80,000, then we would say, okay, wait a second, something went wrong. Okay. Alright. Example 6 is calling back that situation we had in example 1. So Amber wishes to deposit a fixed monthly amount into an annuity account for her child's college fund. So remember, Amber was the one who in the beginning had a lump sum of $73,000 to deposit, but now she's like changed her mind and she said, that is insane. I don't have $73,000. If I split it into monthly payments, how much would I need? So everything's going to be the same. As far as like future value is 150,000. T is 18 years. 18 years. N is going to be monthly, so 12. Payment is unknown, and R. They tell us R in part A. It says, assuming an APR of 4%, so 0.04, how much money should she deposit monthly in order to reach her goal? So we're solving for payment. And that's going to be equal to, 150,000 times R over N, so 0.04 over N, 12. And then in the bottom, 1 plus R over N raised to the n times t, which is 18, and then minus 1. Okay. That gives us $475.30. Okay, so skipping through the calculation there. Okay. Part B says, how much of the $150,000 will she ultimately deposit in the account, and then how much interest is earned? So if these are her monthly payments, how much is she contributing to this $150,000 over the course of 18 years versus how much is the account contributing with interest? So we'll say, okay, so 475.30 times 12 payments per month at 18 years, and that's going to give me, she's going to make $102,664.80. $102,664.80. So that means the interest then, so that's how much she paid from her own pocket, and the interest then will just be the difference of the future value, 150,000 minus this, which is like 47,335.20. So just stepping back from this problem, we see that she'll be contributing about 2/3 of the amount, and the savings account through interest will be giving like 1/3 of it. There we go. Finally, we have example 7, the last example for this section. Says calculating monthly payments for a retirement fund. So assume you have just graduated from college and you have obtained your first job making $44,250 per year. Currently, the national average retirement income for people with a bachelor's degree is $60,000 per year. So that means the average amount that a retired person lives off of per year is $60,000. Well, at least the retired people with a bachelor's degree. Assuming you're 22 years of age when you get your job, you'll retire at age 67. You'll be working and investing for 45 years. At current rates, a mutual fund has an APR of 8%. How much do you need to invest each month in order to live off of that $60,000 per year when you retire? So we know T is going to be 45 because that's how long we're going to be investing. We know N is going to be 12 because we're talking about monthly payments. We don't know our payment, and we want our future value. Well, that's, oh, well, first of all, let me get 8% down, 0.08. Okay. Now the question is, what is the future value? Okay, so when you first approach this problem, you may think, okay, future value, that's going to be determined by how long I live, right? That you may say, okay, if I retire at 67, I get another like 20 years, and then I'll probably die. You know, something like that. It's a little bit morbid to think about, but you might think that is the way to approach this as far as to figure out what your future value should be. But we don't need to approach it that way because we know how much we want to live off of per year. We want to live off of $60,000 per year. So, as long as we make sure that we're earning more than, equal to or more than $60,000 per year in interest, then we'll be good, right? Because if we are putting enough into this account so that after 45 years, it's earning $60,000 per year in interest, then you've just got this lump sum of money that you've saved, and you can live off of the interest fairly comfortably, right? And then that lets you not have to think about how long will I be alive, because you could potentially live forever that way because you're earning at least $60,000 in interest per year. So how can we figure out then what our future value should be? What our future value, like what is that necessary lump sum that we need after 45 years in order for this lump sum to give us an $60,000 of interest. Well, what we're asking is 8% of what number gives 60,000? $60,000. That's what we're asking here. Okay. This is going to give us the smallest number that will give us $60,000 in interest per year at an APR of 8%. So framed as a math equation, this is 0.08 times what number, x, gives $60,000. There we go. Divide by 0.08 on both sides, and we're going to get 750,000. This is the amount that needs to be in our account as a lump sum in our account when we are 67, after 45 years. If we're anything below this, then we won't be earning $60,000 per year in interest. Anything at or above this will be earning $60,000 in interest per year. And every year after that, it would be more interest, right? It'd be more than 60,000. But this is the bare minimum. Okay, so this is our future value. This is future value. So payment is equal to, now that's a big future value too. That's, $750,000. So times, and we're going to have R over N. R is 0.08 over 12, and then bracket parentheses 1 plus R over N, 12, raised to the N times T, which is 45, then minus 1, close that bracket. Okay, so again, doing the calculation, you would do this division, then add 1, raise it to whatever this number is, then subtract 1, hit your 1 over x button, then multiply by 0.08, then multiply by 750,000, and finally divide by 12, and you're going to end up with a relatively small amount of money, all things considered. $142. So if you were able to, once you get a good paying job, if you're able to put away $150 per month with a savings account of 8% interest, then by the time you retire, you're going to be able to live off the interest fairly comfortably, assuming that in 40 to 50 years, $60,000 is still an appropriate amount of money to live off of comfortably. Which, if you've got a spouse and you're both earning that much, then you're talking about now moving into the triple digits, living off of more than $100,000 a year, and, that sounds pretty good. But who knows, in 40 to 50 years, maybe that won't be enough to live comfortably. So, you would have to adjust, maybe make higher monthly payments, or, yeah, anyways, for this particular situation, that is the monthly payment you would need to make. Okay, so for homework problems to mark for review, I just got 2 for you. Number 5 is about calculating a monthly payment, and number 11 is like it's like the very first thing we did, where you're not calculating a payment, you're calculating an initial principal needed. In other words, a present value needed for some given future amount or future value. With, of course, given time period and compounding intervals and APRs. Let's see, is there anything else? No, that pretty much sums up the section. All right, that's it.